All right, so basic definition of addition, just as subtraction is the inverse of addition, division is the inverse of multiplication. All right, inverse operations as it applies to mathematics really just kind of boils down to the opposite operation. There's a lot more to it than that, but that's really the nuts and bolts of it. It's not anything really more complicated than that in terms of a foundational idea, but obviously carrying out the process is a little bit different. Right? For addition and subtraction, for simple values, all you need is fingers. Once you kind of get a sense of the basics, then you kind of graduate to more complicated algorithms and go from there. For division, it's a little bit of a different story because there's so many different ways that you could represent division. Right? So division is the inverse of multiplication, yeah, but we have this division symbol, as you know, where A divided by B is equivalent to B times what is equal to A, right? And so that's kind of the way I always kind of leave things off when it comes to the concept of division. A good place to start is division as a solution to multiplication, right? So when you look at it from that perspective, it's reliant on material that you've already covered, right? So for example, I'm gonna chuck it in over here. If I were to say 10 divided by 5, teaching this for the first time to a student, my first thought would be to say, okay, well, this funky symbol, the one that just looks so weird, yeah, we want to know more about that symbol, of course, but what is it really? Right? 10 divided by 5 is equal to some number. That's really the same as saying 5 times what number is equal to 10. So it's reliant on your multiplication tables, right? So these entries, whatever this is going to be the same as this, right? So then if they know that 5 times 2 is equal to 10, then they would know that 10 divided by 5 is equal to 2, right? So it's pretty basic when you get down to it in that regard, but obviously the bigger the numbers, the more complicated things get. And so it's it can be a little challenging, especially when you get into the different forms of notation, using the dot instead of the X for multiplication. It's an acquired taste. It takes a little getting used to, but once you get the hang of it, things start taking off from there. And then you get into things like the division algorithm, for long division, for example. That's beyond what we're going to talk about in this course. There's a lot of theory that goes into that about why it works the way it does, and it also tends to confuse people. Long division, short division. There's different schools of thought on which one is a better approach to use. I know when I was a student, I think it was 3rd grade to 4th grade. Some things stick out, some things I actually remember from that long ago. But I remember coming back to school in 4th grade and the teacher saying, all right, I want you to try something for me. And she wrote a problem on the board. It was like something not too crazy. It was divide 216 by 9 using long division. We're like, okay, yeah, we learned this last year. We did it plenty of times. We're all good. Everybody sat down to do it. There might have been one person in the class who was able to do it. Everybody else completely forgot how to do it. It wasn't even that complicated of a problem. It's just, there's a lot of moving parts to the division algorithm. Fortunately, it's not something we're going to really get into here, but the idea of using division as, in as many different forms is meaningful. Right? So we'll talk about division as a form of multiplication. Yeah, we got the important things like dividend and divisors and quotients. Most people know the quotient is the answer. They sometimes get confused by the dividend and the divisor. I kind of take the divisor and sort of think of it as a verb. So I sort of change the OR the spelling of divisor into divisor, ER, like in my own mind. So I make it into a verb. So in that regard, I look at it as it's the thing that's doing the dividing, right? So it's the knife that's cutting the dividend, right? That's something that helped me. There's different ways to help people remember it, though, you know. So the example here, 12 divided by 3 is 4, 12 is the dividend, 3 is the divisor, 4 is the quotient. And, just reiterating what I said before, 12 divided by 3 is 4 because 12 equals 3 times 4, all right? So basically, all that whole blurb, the in other words part, is really just saying that if you need to find the solution to a division problem, you could always create an equation, a multiplication equation that allows you to come up with that solution. It's not too far of a cry to get into equation form from here. So based off of my example, so because you got to look at everything you do in elementary school as a building block for the future. So who's to say I can't take these two things, right? Oh, man. Let me get rid of that. And make them x's. Now I have an equation. I have an algebraic equation, right? All I did was I replaced my filled in box with an X. And now you've created a nice little intro to basic algebra. So 10 divided by 5 equals X. I mean, in most cases, people know that you can solve equations using different techniques like dividing both sides by a number, multiplying both sides by a number, adding and subtracting both sides. But this is really kind of getting at the idea that if you were given something like the 5 times X is equal to 10, just think back to any algebra class that you ever took. If you had 5 times X equals 10, how would you solve that? You'd probably take a 5 and divide it into both sides. And then you do the cancellation. Everybody likes doing the little line through it. It makes you feel good. And so you get 2, X equals 2. You probably skip that step. But what are you really doing behind the scenes? You're finding that X is equal to 10 divided by 5. All right, which gets you to this step. All right, but because you intuitively know the division of 10 by 5, there's really no work to do. You just get into the habit of saying, okay, I just divide both sides by 5 and you get it, right? So what's happening is by attacking a problem using this technique, you wouldn't do all that business with X. By attacking a problem using this technique, what you're getting at is an algebraic understanding of the concept, right? So you kind of look at, a lot of people look at it as sort of a waste of time, but it's only a waste of time in your current curriculum because most people really can't think beyond their goals for that current year. It's very hard to think beyond that. And I'll tell you, if you've ever heard the teacher in a class say, well, we can't stop, we're behind. I always kind of chuckled at that because I'll tell you what, in every class I've ever taught, yeah, I'm just making sure I'm not lying. Yeah, I've always been behind. I very rarely finish a curriculum because there's certain points where it doesn't make sense to rush. Like, it's a complicated concept. So I'm going to stop, I'm going to slow down, I'm going to spend some time on it. Why? Because I know, based on the fact that I've taught all the classes that follow the current class, what the important stuff is and what the important stuff, or what really isn't that important. So I'd say, you know what? We're going to skimp out on this concept because we know that this is the important stuff. We're going to stop. We're going to really pay attention to this idea, even if it means we don't get to some of the trivial stuff down the line. Okay? And so you'll see, it's going to happen tonight. I have a whole packet here. We're going to do like 2 more pages and then we're going to call it, because everything else is like the luxury of time. If things broke out the right way, in my mind, it was like, I don't know. I'm not really good with the calendar. I'm like the worst when it comes to that. It was like I try to play it cool, like I know things in advance, but I was probably just as surprised as a lot of you were when we didn't have election day, when we didn't have class. I was like, oh, look at that. What do you know? All right, well, there goes a week, so the best laid plans, that's what happens. So so it is what it is. But by knowing the curriculum, you go through and you say, well, we don't need this. This is important, that's not important. And we can kind of chuck the stuff that's more trivial. The concept of division as a form of multiplication, incredibly important. Right? Can't emphasize it enough. Right? To the point where I actually almost skipped it tonight, and it would have been such a disservice. Right? The example, the floor of a right rectangular solid measure. So that's your classic rectangular solid. I'll try to draw it in a second. I could also copy and paste it from the previous page, but I like to kind of give it a shot at least first. The floor of that rectangular solid measures 3 by 2, and the solid has a volume of 30 cubic meters. What's the height of the solid? All right, so let me get this solid going, and I'll just do it, in the classic sense. A little rectangle with some depth. It's not going to be anywhere near to scale, but that's not important. I mean, it's important to someone. It's not important to me for this particular example. The floor is represented by the measures 3 by 2. So I'll call this one 2 meters. Kind of looks like it could be 2 meters. Actually, I have no idea. I just know that this front side looks a little smaller than this side, so 2 by 3. The height is unknown. This is what I'm looking for. All right, that's this measure here. All right, so volume of a rectangular solid is length times width times height. So I know it's 30 cubic meters. The length is 2 meters. The width is 3 meters. The height is some unknown number of meters. All right. See, what I'm doing here is I'm just creating an algebraic expression on the right-hand side. Just it's more intuitive. Right? The whole thing is algebra. That box can very easily be an x, but we don't introduce the x's this early because I'll tell you what my reason is, and I'll tell you what the standard response is. We don't introduce. So actually, I'll tell you the standard response. The standard response is because studies have shown that the students cannot connect the verbal and the mathematical at such a young age. All right. So when we talk about variables and numerical values, the data suggests that they're just incapable of doing that. All right. So the real reason, in my opinion, I think it's pretty solid. You can disagree if you want. It's perception. It has to do with the fact that the parents remember algebra being hard when they were in school. Right? So the people who put pressure on boards of education remember that algebra was hard. They don't want their elementary school students doing algebra. So what we do is we do algebra anyway, but we just kind of frame it in a slightly different fashion. Right? So I'm using a box here, but we know damn well that's the same as 2 times 3 times x is equal to 30. What are we doing? We're going to multiply, we're going to divide, or we're going to just use our number sense to come up with our solution here. But in effect, it has to do with the pressures put forth by people who really aren't, kind of, if I can be on a soapbox for a minute, educated in education. They just like trig is hard. Oh, I remember calculus. Calculus was hard. Like so they don't want that trickling down into the lower levels. They're the younger levels, I should say. They want it to be just fun times in the elementary school. And so it is, but we have to work to make it fun. Right. And that's all of our goals anyway. We don't want it to be boring. Like, it is my chosen profession. It kind of stings when people say that lesson was really boring. I was like, my stock reaction was, well, sorry. I didn't try to make it boring. Try to make it as interesting as I could. But, I also didn't invent the stuff. So sometimes it really is just boring. In this case, you give them a word problem, they're not gonna get all fired up over it. But if you make it more tangible, you actually hand them the block, then you can get a little bit more interest out of it. In this case, we have 3 of these m's. That's where the m cubed comes from. All right. Now, again, on an elementary level, are you going to explain keep the base, add the exponents? Probably not. All right. What you'll say is I have m times m times m. That's m to the 3rd power. All right. You're not going to really get into anything more than that. It's like 2 times 2 times 2, 8, because it's 2 to the 3rd power. There's no reason to shy away from exponents, right? You just don't want to go too crazy with it, but you can kind of get into the fact, okay, there's 3 of these here, and I'm multiplying it. When you multiply it, that increases the power of the expression, all right? So I would ask myself, what is 2 times 3 first? All right, so self would reply 6. And then I would say, okay, self, 6 times what gives you 30? And then I'm tricking myself into saying, well, 6 times 5 is equal to 30. So then we would say, as a final answer, the height is equal to 5 meters. Pretty huge box. I'm guessing it's probably like, they say a right rectangular solid. All right, 3 meters by 2 meters. That's roughly 6 feet by 4 feet. It's pretty, actually, no, sorry, roughly 9 feet by 6 feet. I don't even know what I was doing. I was just doubling it for some reason. So 9 feet by 4 feet. And then you're talking about like about 15 feet high. So it's a really tall closet, I guess. I don't know. But it's possible. It's definitely not a building block that a student would use as a manipulative in class. Right? But you could also kind of engage the students using that idea. Be like, oh, 5 meters. That's pretty big. Can you think of anything that's 2 meters wide, 3 meters long, and 5 meters high? I can't. And then let them take over the show and say, well, I was in a room one time, and that's how I related to this problem. Or have them come up with the dimensions, and see where that goes. Right? So multiplication as a means of comparison. This is probably one of the more important concepts. I know I say that about pretty much everything, but this is definitely one of the more important concepts because it's multiplication for a purpose. Right? Same idea for division. And I said this before, the word problems are where you really get at the underlying concepts in mathematics. If you really kind of just focus on the skills, this times that, this divided by that, without ever applying it, then you kind of lose the flavor of the concept. Right? What ends up happening is the students get really good at just multiplying and dividing. They never really know why they're multiplying and dividing. Right? I mentioned this last time that I made it into, it might have been my adult life, but definitely older than I should have before I really thought about why I multiply up the price of an item by 1.08 to determine what the final price would be after sales tax. Right before that, it was just like, that's just what you do, right? Which is weird because I remember the activity, I believe it was in 5th grade, where we had, the teacher had newspaper clippings, like back when newspapers were a thing. And in those newspaper clippings, they were like the little inserts that had, the coupons, a sale at Macy's, a sale at this place, 20% off. And so each group got all these different clippings. Now it would just be like a printout probably from a web resource, but it's still available. 80s tea. That's why I was looking for Black Friday. They offered a deal and said 30% off if you spend $100. I was like, oh, that sounds great. That's $30 off if you spend $100. More if you spend more. 30%. That's significant. And then I looked at the individual prices of the T-shirts. And I'm looking at them. I'm like, wait a minute. This shirt that's now $45 was $32 last week. They jacked up the prices on the T-shirts so that after the discount, it ended up being the same amount that it was prior to the sale. I'm like, oh, well, I'm not happy about this, but I understand the math. So I'm not happy because I didn't get a discount on the T-shirts. I just didn't buy the T-shirts. I don't like people trying to fool me. But so there was that part of it. But then there was also a part of it where I was like, I respect that. You use your knowledge of math to try to pull one over on me. And I'm sure they pulled one over on plenty of people, getting them to pay the full price just by telling them that there's a discount. So maybe that's something that you do in your class. Here's the deal. It's 30% off if you spend $100. This is what the price was on November 10th. And this is what the price of the item is on November, 27th, 26th. Like, what's the story there? What's the better bargain? Get the kids involved that way. But like I said, that's the kind of thing that gets them excited about the math. It's not just let me multiply. It's see what you can do. So the exploration here, multiplication as a means of comparison. Jerry, Nick, and Melissa went running one Saturday morning. Melissa ran twice as far as Jerry. Nick ran 2/3 as far as Jerry. So it's a bland kind of problem. But again, you start kind of let the juices flow and you see how you can make this more authentic. Let Jerry's, Nick's, and Melissa's distances be represented by J, N, and M respectively. Right. So we would write an equation expressing the relationship between J and M. All right. So we focus on the key ingredients here. J and M, J is Jerry, M is Melissa. Melissa ran twice as far as Jerry. All right. So interpretation is going to be the key to any kind of word problem. Whether you have them writing equations or not, is not really the point behind this. It's really so much that they would look at it and say, well, okay, what does it mean for Melissa to have run twice as far as Jerry? So you kind of play it out and say, okay, what if Jerry ran 1 mile? How far did Melissa run? 2 miles. Right? What if Jerry ran 10 miles? How far did Melissa run? 20 miles. And you kind of play it out that way. So then you would say, well, is it fair for me to say that Melissa, whatever she ran, is always going to be 2 times whatever Jerry runs? Right? And you kind of throw that out there. And then they get thrown off by the numbers initially. But you say, for example, what if Jerry ran 5 miles? All right. So I have my M equals 2 times J. It would logically follow that M is equal to 2 times 5. 2 times 5 is 10 miles specifically. All right. So you look at that and say, okay, well, that seems to fit what they're saying. So you come up with a guess. Now, if I'm a student, I might not have a single idea how to do this. I look at it and say, okay, well, I got to use the letter M. I got to use the letter J. twice as far, and it's an equation. So equation means equal sign. All right. So maybe you get it backwards. 2m equals j. All right. So you put it, you do a test value. You pop in whatever you think for Jerry and see if it makes sense. Didn't make sense, so you try it the other way around. One of my favorite things to say is you should all try to follow the CAN method of problem solving. Try something, and if it doesn't work, try something else. And that's the thing. I have a lot of students that are afraid, absolutely afraid, to put pencil to paper, pen to paper, unless they know what they're writing down is correct. Right? I have students that when I make a mistake, and it's especially annoying for them when in this situation where I can easily change my answer. You know, like, oh, whoops, I accidentally put 8 instead of a 6. Let me just wipe that out and fix it. They get visibly disturbed by that. They're like, oh, because they want their notes to be beautiful. And I'm like, you know what? Sometimes a little ugliness when it comes to math explorations, note taking, sometimes a mess is a good thing. You know, the scratch work is sometimes where all the good math happens. That beautiful, pristine solution that you get down on paper, that's fine for a final product. But if you think about an English class, you write solution, or not solutions, you write draft after draft after draft. You know, you write your first draft. Somebody takes a look at it and says, awkward phrasing, typo, grammar over here. So then you revise. You revise it up. You feel pretty good about it. You have somebody else take a look at it. What about this? That doesn't really flow. That change you made, I like that idea, but now the paragraph afterwards doesn't make sense as a follow-on. All right, so back to the drawing board there. So you continue working it until you have a final product to submit. Now, you don't necessarily keep a record of all those trials and tribulations as you're revising and refining your paper, but they're all there. And in fact, in Microsoft Word, if you have your own account, you can go to previous versions and take a look, especially in Google Docs, same thing. Go to previous versions and say, oh, that's where this started. You know, for math, people just want to put down the beautiful final answer without the trials and tribulations that went into it. And as a teacher, you kind of lose a lot when that happens. You know, I'll have students that come up to me and they apologize for their test. They hand me a paper with with all the answers questions. It's a mess, like arrows over here, over there, everywhere. And I say, I'm sorry, it's a mess. I made a mistake. I had to erase it. And I attached like 4 other pages to it because I screwed up on the first. I'm like, what are you apologizing for? And I do understand that there are and there always will be teachers along the way that look at it and say, oh, you got the frills on the edge of the paper or whatever they're called, the fringes, you know, from the spiral notebook, take it back, 0. Oh, you didn't box your answer, wrong. You know, little things like that. You know, if you develop a little bit of flexibility to use that buzzword over and over and over again, it goes a long way, right? So suppose Jerry ran 12 miles. Use a diagram to determine how far Nick ran. All right. So Nick ran 2/3 as far as Jerry. All right. So the diagram is kind of tailor-made here. So I'm going to box the whole thing here to represent Jerry. He went the whole shebang, the whole 12 miles. Now, Nick went 2/3 of that. All right. So out of the 12 that's available, out of the 12 miles, we break it up into even increments. We know that we're looking at 4, 4, and 4. All right. We also know that since we broke it up into 3 even increments, that 2 out of the 3 boxes here will constitute 2/3. So I'll get another box going here to represent the 2/3. Right. So just by looking at it, I would say, well, we know that we're going to have a total of 8 miles for Nick. So Nick ran 8 miles. All right. Parents the world over get so aggravated by those kind of questions. The world over. Who am I kidding? That's hyperbole. Not everybody does stuff this way. But they do get aggravated because they look at an answer key. They look at they buy workbooks. They go to engageny.org and they look at the Common Core curriculum and everything that they could find. And then they come across a diagram like this and they're like, what the hell is this? How am I supposed to teach that? You know, it is what it is. It's a diagram to represent a situation. You know, it's getting at a different mode of instruction, right? And we know the 3 modes of mathematical learning and instruction: the verbal, the numerical, and the graphical, right? So, or the visual. So it's just another element that comes into play. So in this case, we're kind of combining the two of the 3 ideas. We have a graphical or a diagram form, and we have a numerical where we're just taking numbers, dividing, adding them together. You know, we got a lot of things going on here. But the one thing you might lose sight of is the fact that there was some intuitive division going on here. So I looked at this and I said, oh, it's 4, 4, and 4. Why? Because 4 plus 4 plus 4 is equal to 12. That's number sense, all right? But it might take students a little more time to figure that out. So what do? You say you have 3 different boxes to carry, you know, to split 12 items among. So what you do is, or what you can do, one way of handling it would be count them off into groups of 2 or 3 or 4, you know, whatever makes sense, or have them count off, right? So I would say, oh, that's a little bit. 1, this would go in box 1, box 2, box 3. 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 All right. And then if you really want to be clever about it, or creative, or whatever the right word is here, put all the 1s in box 1. Now I got a total of 4 there. Put all the 2s in box 2. And all the 3s in box 3. All right, you're just evenly distributing from one group, you know, kind of like a population, into little samples. Right? You can get it that way. Ultimately, it's really up to you how you want to go about it, but like, you do need to get across this idea that there would somehow be 4 miles in each of those little increments, right? Because that builds towards the equation component of it. Write an equation representing the relationship between J and N. Nick ran 2/3 as far as Jerry, right? So whatever Jerry's distance is, take 2/3 of that and you'll get Nick's, right? So a little rephrase on that. Nick's distance is, because is typically translates to equals, Nick's distance, N, oops, a little too thin there, is 2/3 of Jerry's, of translating to multiplication in those contexts. Right? So that's getting at the idea of a proportional relationship. Right? Words that you would not use with your class, but you still want to sort of drive that idea home. Right? So if one variable is only differing from another by a scalar multiple or a constant multiple, then you're dealing with a proportional relationship. Right? So in this case, you know, n would be equal to j, except there's a coefficient in front of the j. Right? M would be equal to j, except there's a coefficient in front of the j. Because of the presence of that coefficient, you're dealing with a proportional relationship. And all of that you're kind of driving at without ever getting into a graph, you know, like an XY graph, without plotting points, without doing all that middle school stuff. It's all just fundamental number sense that's being built just based off of these ideas. Okay? So something is more or less based off of, you know, some kind of multiplier. So then the multiplication and comparison situations, you know, the blurb, you know, it really just kind of gets at that. And more just like elaboration on that, but a couple of examples that go a little bit further. I would be kind of remiss if I didn't get into a percent problem because I've been kind of alluding to that. Right. So the example there, if y is equal to 7% times x, then y is equal to 7/100ths of x. Right. The percent symbol. So as most of us know, I would think, this is kind of common knowledge. Percent of 100. Okay. So when I say 7%, 7% translates into 7 of 100, 7 out of 100, right? So it's essentially a division problem. It's just notation to represent that. It's a shorthand notation. That percent symbol just means whatever that number is divided by 100. In most cases, people know that, but maybe you didn't know the origin of it, right? So if y is equal to 7% times x, then y is equal to 7%, 7/100ths of x, and you know the verbal form of that, right? So if I were to say something like, what is 7% of, I'm a little out of room there, let me fix that. 25. It's really the same idea. Just we would be saying y is equal, we use the same model, y is equal to 7% times whatever the x is. In this case, the x would be 25. So y is equal to 7/100ths times 25. Hey, you'd have to do the work, but you get there. Right? So ends up being 7/4. You know, I don't want to get too crazy into this, but I could just leave it at 7/4, I guess. Not really the point of it. It's really more so that we get into the appropriate form. Just make it a little nicer. All right. So yeah, because the 25 goes into 100 4 times, so it's just 7/4. Doesn't really matter what the form is. It's just 7/4 is 7% of 25. All right. So that's really the idea there. But it's using multiplication as a technique for finding a percentage. All right. So in number 2, when the guest ate 2/3 of a box of 24 candies, it's along the same idea or the same lines, except 2/3 is already given as a fraction. So we don't have that percent issue anymore. It's 2/3 of a box of 24. So it's just a straight up multiplication problem, right? So 2/3 times 24 is going to be 16. Right. But this goes back to what I was saying before. It's like, okay, well, either your students are just going to naturally know that, doubtful, at least in the early going anyway. Or you need a technique that's going to help them get that across. Right, 2/3, I got a denominator of 3, which means I have my total of 24. That's broken up into 3 congruent intervals. All right, so that 24, and again, you could use the dot technique that I did before. It's a lot of dots to draw, but technically you can do it. You'd say, okay, well, I'm breaking up the 24 into groups, into 3 groups. What you could do instead is, use your fingers, because I mean, I've been saying that before, where people said, don't use your fingers to do math. And I'm like, that's not a good thing to say. Use your fingers if it helps. Okay, so 24, you start counting off, and you say, okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and kind of break it up that way and say, all right, so what if I did 1, 2, 3, 4, 5, 6? I think 24 divided by 3 is 6. Right? Do 6 2 more times and see if that gets you to 24. The other way to do it would be to actually count into groups of 3 and see how many groups of 3 you end up creating. I think that's the better way to go. And then once you do that, you're in pretty good shape. So you'd say 1, 2, 3, 4, 5, 6. So that's 2 groupings. 7, 8, 9, 3 groupings. 10, 11, 12, 4 groupings. 13, 14, 15, 5 groupings. 16, 17, 18, 6 groupings. 17, 18, 19, 7 groupings. 17, 18, 19, no, that can't be right. I'm up to 21 somehow. Anyway, so 21, 22, 23 is the 8th group. Somehow along the way I lost count. But that's the idea. You can do it that way. Or if they're comfortable counting by 3s, that's even better. 3, 6, 9, 12, 15, 18, 21, 24. That's 8 groupings of 3. So then you would know that there would have to be 8 in each individual category. All right, a lot of different possibilities, but that's where you have the luxury to make those decisions on your own. All right, now you would need 2/3, and that's going to amount to a total of 16. Shrink it down a smidge. And so you get your 16 that way. Now, technically, when it comes to percentages, you could do it the same way, except it's out of 100, not out of 3. So that means that I'd have to draw a box with 100 little increments, each amounting to 1, just to count 7 of them. All right, now, if it's out of 25, I'd have to break that 25, so a rectangle containing the total distance of 25, I'd have to break that into little increments amounting to 100 separate increments, and then count up just 7 of those evenly spaced increments, knowing that each one of those evenly spaced increments has a width of 1/4 of a unit. That's too much to ask. All right. The idea here is that we use the simple cases to generalize, and then you say, okay, you see how this works for 2/3? How you can just multiply? All right. Well, if it's 100, if it's 1,000 as my denominator, we can still do the same thing without having to draw the picture. Look at that. Now you've generalized. Right? So the exploration. John ordered 8 pizzas for a party. His guests ate 2/3 of all the pizzas, of all the pizza. How much pizza did they eat? For whatever reason, I forgot how to read. Solve this problem by partitioning the pizzas below and shading the pizzas that were eaten. Well, we've got 8 pizzas, and they ate 2/3 of them. Well, we know that we're not going to divide evenly 8 by 2/3. Right, but what we can do is we can break each pie into thirds. spacing's a little off. I was going to say we'll just live with it, but then I immediately started changing it. So a little bit better. Still a little off, but better than it was. Kinda. And that right there is an example of an exponential relationship. That's pretty cool. You know, just a little nifty separate applications. You know, it's the little things that you do. You realize, oh, I'm doubling. So I just drew the symbol once, copied it, and I have it in 2 places, then copied the 2 of them to get into 4 places, and then copied all 4 of them to get it to fill out the 8. And you know, in the grand scheme of things, did you need to take a class, 3-credit class that meets once a week for 16 weeks in order to get that little pearl of wisdom? Probably not. But you know, it's a little nifty little applications of that gets the students, especially in the elementary level, gets them more interested in this stuff. All right. So I have a total, and you could just count them off. So how many pieces do you have? Well, these are generous slices. You know, if you break them up into 8, you know, the traditional 8 slice pies, then you'll have a lot more. But since it's 2/3, breaking the pie into thirds seems to make sense. All right. So I'd count them off 1, 2, 3, 4, 5, 6, and so on. I get 24 slices. All right. Now we're looking at 2/3 of those being consumed. So it's basically the same problem. We'd play it out a little differently though. All right. So what we would say, in my opinion, this is the way I would kind of tackle it. This would be slice 1, slice 2, slice 3. Right? If I want 2/3, what I would do is take 2 slices from every pie. So 1, 2, 1, 2, 1, 2. You know, this is me just illustrating how I would count it off. I wouldn't actually necessarily label them 1, 2, but this last slice would be the 3rd slice. That would be the one that's not getting consumed. Right? So I would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 of those available slices. All right, so 16 slices are eaten. That feels like were more appropriate use of the word were there, I think. All right, now the direction said shade the pizzas that were eaten. All right, so, okay. Now those 16 slices are each 1/3 of a pie. Question said, how much pizza did they eat? We could say 16 slices, but without the context, that doesn't actually really justify what happened, because if you look at it like the equivalent of 16 slices on a regular pie, you know, like you order a pie from wherever, your favorite pizza place, and it's going to come in 8 slices. Right. So if you eat 16 slices, you ate 2 pies. Right here, you definitely ate more than 2 pies if you ate 16 slices. Right. So we're looking at 16 1/3 slices. So I'll say 16 of, that's poor quality of, the 1/3 slices. right? So in this context, well, similar context anyway, I would take the 16 and multiply it by 1/3. And I could get a couple of different representations of the answer. 16/3 or 5 1/3 slice, 5 1/3 pies. Well, I'll say pizzas just to be consistent with the way the question was framed. All right. Now you could do it that way, but if you know, and again, this is all operating under the assumption that the students know how to do these computations. The idea is an exploration. The idea is for them to kind of discover these computations as they go. So what you would say is, right, every 3 slices make a pie. So I got 1, 2, 3, that's 1 pie. It's kind of hard to see. I'll use a highlighter. 1, 2, 3, that's 1 pie. 1, 2, 3, that's another pie. 1, 2, 3, that's a 3rd pie. 1, 2, 3, a 4th pie. 1, 2, 3, a 5th pie, and then we have a 1/3 of a slice left over. All right. So 5 1/3 pies, or 5 1/3 pizzas. All right. So in that regard, you can actually get at the 5/3 without having to do the computation. But then that's the talking point where you say, well, if I know that there were 16 slices and each one's a 1/3 of a pie, isn't that 16 of those 1/3 slices? Couldn't, when we use that word of, doesn't that mean typically multiplication? So when that happens, can't I just say 16 times 1/3? What does that give? 16 over 3. Right. Well, what does that mean? What does that translate to? I don't know. Well, let's investigate. Then you get into conversions and fractions and all that stuff. All right. So 4/5 of the City Council of Newton voted in favor of a tax increase. Of those in favor of a tax increase, 2/3 indicated that the increase should be more than 1%. What fraction of the City Council was in favor of a tax increase over 1%? Right. So, that's the overarching question. So, in the framework of the problem, suppose the large rectangle to the right represents the Newton City Council. Shade the area representing those who voted in favor of tax increase. Well, 4/5. That 4/5 of that population, I guess, voted for a tax increase. So I need 4 out of every 5 to say that they wanted a tax increase. So what I would do, you can kind of look at it and say, well, each row is 5 units, right? So 5 individuals. So 4 out of every 5 are going to be part of my solution. So I would look at it this way and say, all right, well, here's 4 out of the 5. Here's another 4 out of the 5. Let me just use a copy paste. And there's other ways for you to count your 4 out of 5. You do it that way. All right. So another way to do it would have been to say, I'll put that back in a second. I just want to show you. 1, 2, 3, 4, and then say, okay, well, maybe, actually, you know what? Let me do it vertically. It'll be a little easier. I won't have to fake it as much. 1, 2, 3, 4, and then this is the one that didn't vote for a tax increase. 1, 2, 3, 4, and then this one didn't vote for a tax increase. And then 1, 2, 3, and 4, with this one not voting for a tax increase. All right. Either way, you're going to have 3 left over. You know what I can do? I'll save them both. Put this. No, get out of here. A little big, a little too big there. Put this here for a sec. Put this back in. bring this over. Yeah. Oh, it disappeared on me. That would have been nice though. Yeah, I lost some of my. Okay, well, I'll just redraw it. So 1, 2, 3, 4. There's a big old X here. 1, 2, 3, 4. Big old X. Okay. There we go. So either of those would be satisfactory. Stripe the area representing those who favored an increase of more than 1%. All right. So of those in favor of a tax increase, 2/3 indicated that the increase should be more than 1%. So 2/3 of the green here. So 2 out of every 3 said that there should be more than 1%. Right. So what I can do is kind of just go vertical in this regard. Say, okay, down the vertical, I have 3 cells. So I can say, well, here's 2 out of 3. 2 out of 3. 2 out of 3. 2 out of 3. Oh, poor quality 2 out of 3. All right. And so the last part is, a little simplistic. Use the diagram to answer the question. What fraction of the city council was in favor of a tax increase over 1%? Well, it looks like I got 8 cells that are accounted for based off of first being in the 2/3, I'm sorry, in the 4/5 group, and then also being in the 2/3 group. So I have 8 out of the 15 available. And it asks for what fraction, so we're good. We just want to make a fully functioning looking 5 there. All right. It would definitely be a little bit trickier to do with my purple diagram, but still manageable, because then what I would say here is, okay, out of the all of the purples, ignoring the red X's, now let's focus on 2 out of every 3. So I could say 1, 2. It's a little hard to see, but and I give a big old red X here. Kind of a mess. Let me do a different color, something vibrant and bright. So 1, 2, not this one. 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 Let me just make my shading a little bit more pronounced. And then you count up all the ones that are shaded in completely, or as completely as I opted to make it. All right. And from there, you can see that there's a total of 8. All right. And so 8 out of the 15 available. I know this one's a little messier, so the other one is definitely the way to go. But that requires you to have a shading tool, so that's a little bit of a different story also. Right. So that's a technique that you can use that doesn't involve saying, all right, 4/5 of the city council. Well, what's the city council? I mean, essentially, you're just multiplying. You have 4/5 multiplied by 2/3. That gives you 8/15. But this is getting at the idea that there's a multiplication. When we say a percent of a percent or a fraction of a fraction, it's talking about multiplication, right? And that allows us to kind of, I don't know, I would say probably sort of cut to the chase a little quicker. So the next one, where it says, solve the following problem by using 15ths as the unit. So 2/3 times 4/5 is equal to 2/3 of 12/15, which is equal to 2/3 of 12. This it's kind of like whoa, what's going on here? But if we carry out each of the multiplications, you can kind of see how it plays out. So just kind of off on the side here, let me show you real quick. Make it a little smaller, a little darker. So this is 8 over 15. The 2/3 of 12/15 is equal to 24/45 if you just straight up multiply, right? But that's a fractional equivalent to 8/15. All right. So it's really getting at the same idea, 2/3 times 4/5 and 2/3 of the 12/15. So that 2/3 of the 12/15 comes from what we shaded off in green initially, and then taking 2/3 of that. But multiplying it gives us something that looks like, whoa, where do we get this 24 out of 45 from? But if you reduce that, dividing top and bottom by 3, you get 8 over 15 anyway. All right. So the 2/3 of 12 gives you the 8. Oh, that's a little typo. This line shouldn't be there. All right, so if you just focus on 2/3 of the 8, we would be looking at 8 out of 15, or 8/15. All right, so what this is getting at is the idea, and I'll just kind of, I tried typing it, but obviously I screwed that up. So typing and me not so good together. But if we take 2/3 and multiply it by 12/15, what we're getting at is the idea that this is the same as saying 2/3 times 12 times 1/15. And that 12 times 1/15 is the same as 12/15. All right. So we could break that up into its product of it itself and its unit fraction. All right. So, or the numerator and the unit fraction, I should say. By the commutative property, we can now say that 2/3 times 12 gives us a result of 8. Right. So essentially, I'm saying, okay, well, I know that 12/15 is equal to 12 times 1/15. Let me just, oh, actually, I'm sorry, not commutative property, associative property. We can change the order of multiplication, but we could also change the grouping within that order of multiplication. So either way, it'll get the job done. But 2/3 times 12 gives you the 8, which when multiplied by the 1/15 gives you the 8/15. All right, so that's kind of a lot of stuff to take in. Obviously, you wouldn't do that on day one with your students, but it's something that you definitely want to work towards. All right, so that would be, and I'm just going to try to sneak it in down here. 8 times 1/15 gives you the 8/15. That's what that little typed up expression there was supposed to say. It didn't really kind of play out the way I wanted it to. All right, so it really kind of gets at that shortcut idea. All right, so that next part doesn't really make sense now that I went over that example. So we'll get rid of that and call it a typo. So somebody gets some typo bonus here. And so it's really a 3, not 3A and 3B. All right. All right. So I'm going to stop the video here, stop the recording.